Hello everyone, welcome to this lecture. In this lecture we're going to learn how to do some basic calculations using circuits and its components. But first we need to learn some basic things. First thing is that how we choose a direction in a circuit, choose a direction of current and circulation direction. I'll explain what I mean by that. So first recall that we had a formula that is VB minus VA equals minus sign integration of A to B E dot ds, and this formula is the potential difference between point A and B when I am going from point A to point B. That is, A is the initial point, B is the final point. And for closed path, it's just integration of this circle means the closed path integration. E dot ds is actually 0, and that gives us sum over I delta V of I equals 0. Delta V of I is the potential difference across different elements in a closed path, across different objects, you might say. So given this, let's draw a simple circuit and consider some situations. So this is a symbol for battery, and say we have a resistance right here. Resistance is say R. So this battery is like complete. So this is a plus terminal, this is the minus terminal, and this is the EMF of this battery. So since plus terminal is in higher potential, we say that current is flowing from this say higher potential terminal, so this point A, in this direction through this resistor. But so this is the direction of the current we chose, but this is not very straightforward in every circuit. For example, if you had, say, on battery one resistor and another battery here, EMF of the first battery is E1 and second battery is like 2. So in this circuit, how do you know the direction of the current beforehand? Because you don't know the potential which is bigger, E1 or E2. So so in a general sense, you need to choose the direction of the current. So number one, choose the direction of the current. So two things can happen here. If at the end of the calculation I is positive, remember this is at the end of the calculation, then the direction, so this is the direction I, so the direction of current is as shown in this figure. So this is case A. So case B, so case B is that if at the end of the calculation I is negative, then the direction of the current is opposite than what is shown in this figure. So the direction, this implies the direction of the current is opposite than what was chosen before. What was chosen initially. Okay. So this is one point, and second point is that we need to choose a circulation direction, because we're considering a closed path in this formula. So in a closed path you can move from point A. So let me draw some other points. So point B, say point C, point D. So you can move from point A to B to C to D, then to A. You can also move from A to D to C to B, then to A, then back to A. So both are valid. So you need to choose the direction beforehand to do calculations. So second point is that choosing the circulation direction. This is important because we want to calculate the potential difference across different elements of a circuit. So potential difference across different elements. So say this is one element, and say this is two terminal A and B. So given this element, how do you calculate the potential difference? Do you say VB minus VA or VA minus VB? What is correct, what is wrong, we don't know beforehand. So we need to choose a circulation direction, then we need to apply some rules, and at the end of the calculation we'll be able to find out what is the actual expression for potential difference. Choosing a circulation direction enables us to calculate the potential difference or voltage difference across different elements. I'll show you what I mean by that. Suppose I have a circuit right here. Say this is my circuit and this is the resistance. So this is the plus terminal, this is the minus terminal. Epsilon E is the potential, E is the electromotive force, and this is the resistance. We choose this current direction of the current, and we choose this as the circulation direction. I'm denoting it as CD, means circulation direction. So across the single element, that is the battery, you can draw it like this. So the minus terminal is the plus terminal. If our say circulation direction is like this, CD, then we can calculate the potential difference delta V, which is this V at this point. This is the final point or after point. So after, before, that is, we're moving in this direction. So V after V before. So in this way we can easily calculate potential differences across a battery. So when using Kirchhoff's law in a circuit, the issue that arises, whether we should choose plus sign or minus sign, resolves if we choose current direction and circulation direction and follow some rules. So let's do a simple calculation for a battery. Things will get more clear, I hope, after this calculation. So for a battery, say this is my battery, this is the minus terminal, this is the plus terminal. The electromotive force is given by E, and say I'm going from this point to this point. So this is my circulation direction, and this is before or initial point, and this is after or final point. So then how do we calculate the potential difference? So delta V of a battery is the potential at the final point, so that is V after, minus potential of the initial point, that is V before. Since we're going in this direction, this is our final point, and by definition this is exactly the electromotive force E. And say this is our case 1, and let's consider another case. Say this is our battery. This is the plus terminal, this is the minus terminal, the plus terminal electromotive force, and here we chose our circulation direction in this direction, for example. So here this is before initial point and this is after the final point. So delta V of this configuration in this chosen circulation direction will be V battery equals V after minus V before, because these rules doesn't change, always V after minus V before. But recall that our definition of electromotive force was difference between higher potential and lower potential, that is V higher potential minus V lower potential. So we'll have a minus sign, then our electromotive force, which is the potential difference. So this is the case 2. By choosing different circulation direction, we end up with additional minus sign. Let's look at the case of a resistor and what happens about the potential difference in the resistor. So this is the case 3. So say we have a resistor here, and let's choose this. Say this is point B and this is point A. I'm just choosing the points randomly, and our circulation direction is in this direction. So this is before, this is after, and resistance is R. Direction of the current is, say this is our direction of current. I'm just choosing this direction. So the potential difference across this resistor will be delta V of R is V after minus V before equals, now recall that current always flows from higher potential to lower potential in a circuit. Therefore the potential at B will be in value of potential at B will be higher. So that is, this V before is a larger number with a minus sign, and V after is a smaller number with a plus sign. So according to the Ohm's law, we'll have IR and we'll have this minus sign. And case 4 will be, we have a resistor and this direction of the current. This is our point B, this is our point A, and here, so this is our circulation direction. So this is point before, this is after, and we'll have delta VR equals, so I'm gonna write using a shorthand notation here. So V after minus V before, therefore VB minus VA, and here it would have been VA minus VB. Just I'm using these A and B labels as index here. So this will be plus IR, because VB is the higher potential, because current is flowing in this direction. So it's the larger value with the plus sign and smaller value with the minus sign. So ultimately we'll have a plus sign here.